Alright, let's get into some examples here. So we're going to start with a deck of cards, walk through a few different types of questions that you might see. But yeah, we'll start with the deck of cards, and they're laying out for you everything about a deck of cards, which I feel like most people know, but there's always a lot of questions on cards. So make sure that you know that there's 52 cards in a deck, 4 suits, 13 cards in each suit. It sounds basic, but every once in a while you'll get tripped up, put 50 cards instead of 52 or something like that, and that will lead to an incorrect answer. So, just want to go over that real quickly. Now, I gave the example previously of drawing 4 aces in a row, and I kind of like that one, so I'm going to draw it out a little bit. So I do apologize once again. I had to write this on hand and upload screenshots, so it's a little all over the place. But we're going to start with the odds of drawing 4 aces in a row with replacement. So, let's start over here. We have the probability of drawing an ace one time is 4 out of 52. There's 4 total aces in the deck, and that's going to be down here. Let's look. 4 aces in the deck, 4 outcomes in our event, which is to draw an ace, and 52 possible outcomes. 52 possible outcomes. Now, on the second draw, second time here, we have replaced that ace. So we draw it, look at it, put it back in. Our odds do not change. We have 4 over 52 again. Same with the third time and the fourth time. So, do we add or multiply? Well, the question we're saying is the probability that we have 4 in a row. That is the probability of an ace on draw 1, the probability of an ace on draw 2, and the probability of ace on draw 3, and the probability of ace on draw 4. Anytime you hear "and," you're thinking multiply. You have to have these events occur simultaneously. As you'll see, it leads to a very small number. It's really hard to get that to happen. That's kind of the key of the "and" problems. So you end up with 0.000035. That's 4 zeros. Now, without replacement, we're going to draw a card, leave it out. Set it up the same way. You have 4 ways to get your event of interest, which is drawing an ace, and 52 total outcomes. On the first draw, you have the same probability. On the second draw, though, you're going to have 1 less ace that you can draw and 1 less card in the deck. So you now have 3 over 51. And that will just continue on. So the probability of drawing 4 aces in a row, still multiply, is 4 times 3 times 2 times 1 over the diminishing total outcomes. Now notice, if it was probability of 5 aces in a row, the 5th one would be 0 over 48, and the probability would be 0. You cannot draw 5 aces in a row without replacement. Alright, our next example here. So this question says the sample space S is the whole number starting at 1 and less than 20. That's going to be, well, let's break it into pieces here. Our sample space S is letting the event A equal the even numbers and event B that's the next part. Our sample space alone, it's whole numbers. So it's a set, it's discrete outcomes. We have 1, 2, 3, 4, 5, all the way up to not 20. It does not include 20. So we have the following, 1 to 19. Then it says let A be the event that we have even numbers, and B the numbers greater than 13. And as we see, A is equal to 2 through 18, even, and B is equal to 14, 15, 16, 17, 18, and 19. Next it says probability of A and probability of B. Well, probability of A is 9 over 19, right? There are 9 total numbers in here and 19 total possible outcomes. 9 over 19, assuming that each one has an equal probability. Same for B. Well, what about A and B? Now, this is not asking about the probability, it's asking about the total outcomes, or the event, the outcomes corresponding to that event. Well, it's the overlap in between the two. 14, 16, or 18. Those are the only numbers that are in both A and B. For A or B, we're going to add them together. Now, probability of these are very similar. We're just going to say 3 total outcomes of interest over all the total possible outcomes, 19. Probability of A and B is equal to 3 over 19, and the probability of A or B is equal to 12 over 19. And just, well, we'll just continue here. Now, it's asking us for A's complement. Remember, the prime is complement, and then the probability of that complement. So we already know that A is equal to this right here, the even numbers. So it's asking us for the complement, which would be the odd numbers. The odd numbers are 1 through 19 odd. And the probability of those are 10 over 19. This is an important double check that we always want to double check. What is the probability of A and its complement? It's 1. That's all the probability that we end up with even and all the probability we end up with odd. They have to equal 1. And lastly, this is a little direct application of the A given B formula. We know probability of A and B. We know the probability of B. You simply plug them in and you end up with 3 over 6. Same thing with probability of B over A. We want to know the probability of B given A. Well, we just plug them in. Are the probabilities equal? No, they are not. That is just kind of an interesting little bit that, that does not necessarily mean that they are reciprocal. And there's our final answer. Okay, our last example here. Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A is the event he is successful in his first attempt. Probability of A is 0.65. B is the event he is successful in his second attempt. Probability of B is also 0.65. He tends to shoot in streaks. That's an important key here. The probability that he makes the second goal, given that he made the first goal, is 0.9. So this is going to require us to use this formula. It says, what is the probability that he makes both goals? And what is the probability that Carlos makes either the first goal or the second goal? Let's take a look here. Problem is asking you to find probability of A and B, which is equal to the probability of B and A. And since we know probability of making that second shot B given the first shot A is 0.9, and the probability of B and A is equal to probability of B and A over probability of A, because these are, we can just switch this and switch that to an A, and that gives us the same exact formula. This is all just algebra of the same thing, and if we want to find probability of B given A, we just switch the B's and the A's all around. And that's going to give us 0.585. He makes the first and second goal with the probability of 0.585. Now it's asking us to find A or B. What's the probability we make either one? Notice that this probability is higher. Carlos makes either the first goal or the second goal with probability 0.715. So once again, we're going to add and then subtract the double counting, which is the probability of A and B. This is straightforward. We know the probability of A, we know the probability of B, and we know the probability that he makes both, which we already found above. We're just going to add, subtract, straightforward application of that formula. Then it says, what are the probability that A and B are independent, it asks, are A and B independent, and are A and B mutually exclusive? Now we're just going to test the rules that we already were given above in the previous video. So for C, no, they are not independent because probability of B and A is equal to 0.585. And we know that probability of B and A is not equal to the probability of A times the probability of B, which is this piece right here. So we're just looking to see if this rule breaks. It does. We know that. Thus, it's not independent. You can also do this with a thought logic instead of math, and that's okay as well, but yeah, this is just plugging in these numbers. And lastly, we have the A and B are mutually exclusive events if they cannot occur at the same time. Are these mutually exclusive? No, because probability of A and B are 0.585. You can make the first and make the second. They are occurring at two separate times. It's not either a make or miss. They are two separate events, and thus they are not mutually exclusive. Making the first does not mean that he cannot make the second.